Beautiful.
Hello.
Hello.
Okay, welcome back everyone. And so this is the, I start with the portal first. And on the portal, you see that there would be, oh, let me bring up the mask so that it's better to focus your attention to the part that I'd like to mention. Here you would have, I have started part B. Okay, part A is from week 1 to week 8, and part B is from week 9 to the end. I split into 2 parts so that it's not too long to load the Google Doc. Okay, so that's a, and then you have over here at the top, let's see, would be the link to the midterm feedback for survey form. So please do fill out, because I'd like to find ways to increase your your learning experience in terms of productivity and enjoyment. Improve that if possible. So please fill out the form. And so yeah, you can access part B also from part A. Okay, so let me leave at 100% resolution so you can see the big picture. So at the top of part A, you can also access part B. And if you go down to the bottom, below exam 1.2, you have also a link to part B. Okay, so you can access part B from various documents, and from part B you can also go back to part A right at the top. All right, so this is week 9, and that's the beginning of part B of my daily lecture summary. And so let me zoom into Fit so you have a better view. Okay, so these are the things that I'd like to address today. So it's good to bring up the mask. Okay, I have already, okay, so this week I'm done. Okay, the seating. Yeah, I shuffled the seating so that everyone has a chance to get closer to the screen if you like, but feel free to sit anywhere you like, except that for the lecture summary at the end, you just go back to your team, where your team would sit. But there's a lot of free seats. Just sit anywhere you like. Some, like Kevin and Tony, prefer to be close to the screen. That will be fine. I have already mentioned about the midterm feedback form, so please do so. And let me quickly answer Kevin's question just at the beginning of class. He asked, where can you find the future lecture notes? Okay, I have the whole collection of my lecture notes in the list of topics. So if you'd like to print ahead or look ahead, you can go to the list of topics and print out, because Kevin, he prefers to have one PDF page per hard copy page instead of 4 on 1. So it's up to you. You can also go back to the fall 2014, and then you can sort of see ahead. I don't do exactly the same, but more or less, you get the idea. Okay, so that's regarding the lecture notes. Pretty stable. I worked a lot last semester, so for this semester, pretty stable. Meaning that I don't have a lot of updates. Okay, So the next topic would be, let's quickly, let me see, so I have already addressed this issue. As you see, I move the teams around. Yeah, the list of topics that are covered, and this was what we did in week 7 before week 8 of the exams. I want to address a few remaining issues, particularly the critical thinking questions. These are excellent questions. And so this is a meeting, let's see here, meeting 17, where I have presented to you 2 methods, right, to transform a generalized eigenvalue problem to a standard eigenvalue problem. And you recall that the exam was on method 2, where you absorb the eigenvalue beta with the coefficient 2 of the mass matrix and call it the new eigenvalue gamma for the standard eigenvalue problem. But that is for the type of problems that's very particular kind of mass matrix that is a multiple of the identity matrix, meaning that you have a factor times the identity matrix. So that's a very particular case. And Jackie of Team 9 asked an excellent question, and that's what I put down here. Okay, and I will bring up the mask so that you can focus on this excellent question. What if you have the mass matrix? Well, Jackie gave this number, but it's not necessary that you need to really use this lengthy number. The mass matrix M is a diagonal matrix with the diagonal coefficient 7.4037 and then 1.7985. Well, in math, you don't really need to give such a scary or overly complex numbers to understand the gist of the idea or the principle behind the ideas. Okay, so let me demonstrate by giving something much simpler but have the same characteristic, and that is the following. Because essentially the mass matrix, so here we can still say that, let me, P2 standard eigenvalue problem with more general mass matrix, but still diagonal, okay? In fact, the mass matrix need not be diagonal. When you take a finite element, and let's go something called consistent mass matrix, okay? But here, let's just, okay? And an example would be as follows. You recall that in the model problem with three strings in series and 2 masses, you have the mass M1 and mass M2, right? Need not be equal. And an example would be, for example, let me choose number 4 and 9, because you will see that it's easy to take the square root, okay? And that's enough. This is a case where mass M1 is different from mass M2. That's all. You don't need to have, a long number of decimal digits. It's unnecessary. So here, this is an example where the mass matrix is not a factor times the identity matrix, right? So how do you transform this, the generalized eigenvalue problem, the matrix K, the stiffness matrix K, you can give anything you like, or you can give just like in the exam, or actually the matrix, the stiffness matrix in the exam was a stiffness matrix that I already used in a previous lecture. Okay, so if you review, you would see that when I solved the standard eigenvalue problem, I did use this matrix. So this is not anything that is unfamiliar. Okay. So say, for example, in this case, how do you transform a generalized eigenvalue problem, which is written as k phi equal to beta m phi into a standard eigenvalue problem, right? So now one cannot use method 1 nor method 2 anymore. It's impossible to do that because you cannot either there's no common factor times the identity matrix. Okay, so and so there are 2 more methods that I call method 3 and method 4. Method 4 is an ugly method, meaning not nice. And even though it looks simple, but when I say ugly means that when you do large size problem, right? 100 by 100 or 1,000 by 1,000 or 1 million by 1 million, this is a very, very bad method. It looks simple. Okay, for a 2 by 2 system and diagonal mass matrix, it's simple. So many textbooks led you to this method, but it's not something that is really recommended for large scale computation. So let's do this ugly method first because it's simple, but not nice. Okay, and the reason is because actually, maybe let me leave this as a critical thinking question for the class to participate. And let me do the method first and then you'll see. The method is actually very simple. You start with this generalized eigenvalue problem. So let me just reproduce it here, right? And you just, now you need to assume that the mass matrix is invertible. Okay. So that means that M inverse exists. Okay. So let me write here M. Okay, critical thinking question. What is the condition for the inverse of a matrix to exist? I hope somebody must know. This is a very basic issue that we didn't, right?
Yeah, is it the determinant can't equal 0?
Determinant should not be equal to 0. Okay, so when determinant of M is different, is not equal to 0. It will be like this. And this check out, right, for the example here, the determinant of, let me just put it down here so that you don't mix up the particular example with the general case. Okay, so here, in this example here, determinant of the mass matrix would be different from 0, right? 36 at least. Okay. So what would be the inverse of the mass matrix in this example? This is a very simple example. You can get the inverse immediately without even need to refer to the formula that I already showed to you before. So let me put what team number?
Just 1/36 times.
Dylan, what team
team
number?
three.
Team 3?
Yeah.
So for this particular example here, what would be the inverse of the mass matrix? Someone?
Isn't there just
No one?
1/36 times? Which way do you diagonalize it?
Okay, so
Is it this? Is it
so
4009
okay.
or 9004?
okay.
I don't remember which one it is.
Yeah, okay. Tony wanted to use the general formula, so let's recall the general formula. And remember, I do not memorize this one. Okay, in my head, I follow a definite algorithm. No, let me define the matrix A first. Okay, so A is, let's
you wanna
define
be all
A
the
to
way.
be A, B, C, D, right? Then A inverse is 1 over the determinant of A, and then you get into
Oh.
matrix theory that involves the minor and major and
You
all
wanted the
of
whole
that.
transposed.
Yeah, so
part.
that would be
My bad.
D, A, and then minus C, and minus B here. Okay. All right. But if you apply this formula, what do you get? What is the determinant of A? Tony?
Determinant of A would be 36.
Right.
So 1/36.
So that's 4 times 9, right? And so D would be what? D is 9, right?
Yeah.
What is A?
0 or 4.
A is 4, right? And BC would be 0. Okay. What would be the result? Is it 1 over 4 and 1 over 9 here? Okay. Meaning, you don't really need to apply the general formula in the case of a diagonal matrix. The inverse is immediate. It's just the inverse of each of the diagonal coefficients. Very quick. Okay. So, and you can verify by multiplying the inverse by the matrix itself. And you see that indeed, taking the inverse of the diagonal coefficient is the inverse of the matrix. Okay. So keep that in mind. Now the next step is is to pre-multiply, right? Because the idea is to make the mass matrix to become identity, right? So if you pre-multiply the generalized eigenvalue problem with M inverse on both sides, then M inverse times M is identity. Okay, so that's the idea. So you you take let me copy the whole thing here so I have the formula to work with. So here, pre-multiply the pre-multiply meaning multiply from in front, okay, with M inverse And so what do you get? You get an inverse. And let me move this out. This is beta is a scalar, so it would not affect. You know, you can pull beta out. That would be it, meaning in front of M inverse, and then M inverse here, right? Okay, on both sides, and therefore you get the identity matrix here. Okay, so therefore the new standard eigenvalue problem and for those of you who are taking vibration, you want to pay attention to this, because eventually when you get the multiple degrees of freedom system, you will need to do this. Okay? And you see, we already finished in this course. In the first half of the semester, the multiple degrees of freedom system, in which the vibration course has not addressed yet. Okay. So here the standard eigenvalue problem is written as K bar, a new matrix. K bar, you can use, let's say, using the new notation. For both the eigenvectors and eigenvalues and eigenvectors, okay. Now what is K bar? K bar is a new matrix that is nothing but M inverse times K. Okay. And what is beta? What is gamma? The gamma is the eigenvalue for the standard eigenvalue problem, and that would be equal to beta. Okay. And likewise, C of psi, the eigenvector for the standard eigenvalue problem is the same as the eigenvector for the generalized eigenvalue problem, the original generalized eigenvalue problem. So this is a simple method because you just need to invert n, and in the case of a diagonal mass matrix, the inversion is simple. You don't even need to apply the general formula. You just invert each of the diagonal coefficients, right? And pre-multiply by M inverse on both sides, you get the standard eigenvalue problem. Now let's go back to the reason why I said that this is not a nice method. Okay, this critical thinking question here. So let me rewrite it here. Let me do this so that you have both the generalized eigenvalue problem and the standard eigenvalue problem inside. Anyone? Let's see. To like it. I need to remember your name.
JR for John.
What team number?
Team 4.
Team 4. And what's your name?
John.
John. Okay. Yeah, go ahead.
Because it can be hard for a programmer to find the inverse of a big matrix.
Because the inverse of a matrix?
It can be hard to calculate.
Harder to calculate.
It takes a lot of memory.
In general. Yeah, that's true in general. When the mass matrix is not diagonal. When the mass matrix is diagonal, it's cheap. It's just inverting each of the diagonal coefficients. How about Kai?
Same thing about
Same as what John said. Okay, Kai, you are team 6, right? Let's see, right? Kai, team 6, right?
Mm-hmm.
Yeah. Okay. Yeah. Actually, there's a more a deeper reason why this is not nice is that it destroys symmetry. M inverse times K is no longer symmetric, and symmetry is beauty. You know, because computationally, if you have a symmetric matrix, it's very efficient. Okay, and when I say computationally efficient, I'm thinking 100 by 100, 1,000 by 1,000, 1 million by 1 million, not 2 by 2. 2 by 2 is just for the student to know, okay, the principle. Okay, but even for a 2 by 2, this, can someone demonstrate to the class that M inverse times K is non-symmetric? This is a great critical thinking question here. Okay. So anyone while I type this? Is more time consuming. Anyone can show that K bar is no longer symmetric? Well, you know, what is the characteristic of M inverse? I mean, in terms of the topology of the matrix, it's still diagonal, right? So you can take a simple example. Let's say, or you know, I can do it directly here as well. You have here 1 over M1, 1 over M2, right? 0, 0, and times the stiffness matrix that has K11, K12, K21, K22. Right? You don't even need to put in any numbers. If you write like this, right, and you multiply this diagonal matrix to this matrix, this is symmetric with K12 equal to K21. You know, let's take the first row, right? 1 over M1 and 0 times the first column, you have K11 divided by M1. Okay? Now take the first row and times the second column, you have K12 divided by M1. So that's the first two columns. So the effect of pre-multiply by a diagonal matrix is like, you know, multiply each row by the corresponding diagonal coefficient. So it's like this coefficient multiplied by the first row, and then this coefficient multiplied by the second row. Okay, you can work out in your head. So the result is the following. The result is K11 divided by M1, K12 divided by M1, and then K21 divided by M2, and K22 divided by M2. Okay. Now, can someone, this is a hint, right? You know, symmetry means that K12 equal to K21. Can you see now that this is no longer symmetric?
Mm-hmm.
Because even though K12 equal to K21, but M1 is not equal to M2. That's it. QED. Okay. So here you can, and and that's the reason is because M1 is not equal to M2 in general. Alright, that's how you lose symmetry. And so that's method 4, which is simple, but not really used for large scale computation. And so now method 3, more advanced, complex, but would lead to a symmetric matrix. Okay. Or let's say a new symmetric stiffness matrix. And this you learn a lot of matrix algebra here, including vibrations, okay, dynamics, because this is actually used in large scale computation. It goes as follows. You know, so you recall that M, okay, is a diagonal matrix, can now be split into it's like the square root, you know. Okay, so what is m to the power 1/2? M to the power 1/2 is simply m1 square root m2. Okay, 0, 0. Right? So now you can verify by taking m to the 1/2 multiplied by m to the 1/2. You really need to know this by now. Okay? When you multiply two diagonal matrices, it's just that the diagonal coefficients would be multiplied by the corresponding diagonal coefficients. Okay? Please be sure that you know this. If not, then verify on your own. And if you have problem, please come to see me. I'll be happy to explain. But you need to know this. Okay? This is like 2 + 2 = 4. Or for that matter, square root of m1 times square root of m1 is m1. Okay. So and so let's go back to this example. So just to give you a very concrete example. So that's why I choose 4 and 9, right? Because I know that square root of 4 is 2 and square root of 9 is 3. And I don't need to take you know, lengthy numbers like Jackie suggested to really understand the principle. Let me get rid of this. That's okay. Yeah, let me just compact this so I have more space. Okay, then the square root is simply 2003, right? So that's very simple. So now the next issue is how do you transform the generalized stiffness, generalized eigenvalue problem. Let me zoom out so you have the big picture. It's all the way up here. So let me copy the generalized eigenvalue problem again. Down here. Okay, anyone? How do you transform this generalized eigenvalue problem to a standard eigenvalue problem? Very similar to method 4, at least first step. Remember, what's the goal? The goal is to make this mass matrix to become an identity matrix, right? And also to have k-bar symmetric, the new k-bar, the new stiffness matrix. So here you need a multiplicative decomposition. It's called multiplicative decomposition. So how about pre-multiply by m to the power minus 1/2? Okay. At least you get rid of half. Okay. So let me copy down here. By m to the minus 1/2. That means the inverse of m to the 1/2, right? And by now you know that inverting a diagonal matrix is cheap. You just invert each of the diagonal coefficient. So active learning credit opportunity. In the case of the example up here, yeah, maybe let me be sure that what would be m to the minus 1/2 without going through the general formula. Anyone? Yes. Remind me of your team number and your name. Caleb, is that Caleb? Okay. Caleb is team
5.
5. Okay. Yeah, Caleb, go ahead.
1/2, 0, 0, 1/3.
You just invert each of the diagonal, right? So m to the minus 1/2 is simply 1/2 and 1/3 as the diagonal coefficient. So here 1/2 and 1/3. 0, 0. All right. So that you know. Yeah, so let me pre-multiply by m to the minus 1/2. So I take this generalized eigenvalue problem, right? I pre-multiply by m to the minus 1/2. I forgot, yeah. This vertical bar here, and again here I can move this out a little further. I put m to the minus 1/2 here. Yeah, and let me leave it here so that you can see the thought process, and replace m by this decomposition down here. And then you see that you can cancel half of it. So meaning that the result is equal to beta m to the plus 1/2 times phi. Okay. So you get rid of one factor, but still, this is not symmetric for the same reason that I explained. If you take a diagonal matrix times multiply by a symmetric matrix, this is not symmetric, right? And then on this side, you don't have the identity yet. It's still m to the minus m to the plus 1/2. Okay, so there must be some additional mathematical alchemy to really get that, and this is very beautiful. Okay, you can define m to the power 1/2 as psi, the new eigenvalue, and so therefore what would be phi? Because on this side you need to replace phi or phi, in terms of something that has psi, right? So if you define psi of c, like the Greek would say, equal to m to the 1/2 multiplied by phi, then what would be phi in terms of c? What would be phi in terms of psi? Critical thinking question here.
Psi times m to the negative 1/2 equals phi.
Very good, Kevin. So Kevin said psi times m to the negative 1/2. Anyone who would like to build on what Kevin just said? Kevin is team
7.
7. Thank you. I was about to say Kevin team 6. But,
Yeah.
Okay, so this is Kevin team 7. Anyone? Kevin said phi or phi would be equal to psi times m to the minus 1/2. Anyone would like to build on what he said? Okay, let me write down what Kevin said, and then you can.
That would be the inverse of m to the minus 1/2, right?
Yeah, m to the minus 1/2 would be the.
Or m to the inverse.
So you said
Yeah.
phi is equal to c times m to the minus 1/2, right? Anyone else? Do you all agree with Kevin?
Yes.
Kevin, of course, wish that the class agreed.
Oh, I don't
Okay.
care.
Anyone? All of you agree?
Shouldn't it be the other way? M to the
Very
minus
good.
1/2.
Kevin,
C?
Kevin answered himself, matrices are not like numbers, okay? The order is very, very important. This is the way you think. If you want to move this to the other side, pre-multiply by m to the minus 1/2, so that you can have identity over here. So you see that it has to be multiplied from in front. If you do like this, if you multiply from the back, you cannot cancel this one. Let me give the right solution first. Okay. And the way to think is you pre-multiply, okay, to obtain the above. Pre-multiply both sides by write down here by okay to have, and so here is how you would do. Okay, do not memorize. That's why I keep saying do not memorize, because memorization would lead to errors. Move this out and move this out. You need to understand why you do certain operation. Okay, and only by this legitimate operation that you would obtain the identity here. Okay, now let me give you the other case where what if you post multiply by m inverse, right? I mean, one has to understand why things were right and why certain things were wrong, right? It's not just memorizing the right answer, but one has to think why certain answer was wrong. So here, if you take the same matrix equation and post multiply, right, both sides by m to the minus 1/2, right? You have on this side, you have on this side. But clearly, you cannot cancel these two. Matrices, you know, if you have a matrix in the middle, thank you, Casey. You know, you cannot say that m to the 1/2 times m to the minus 1/2 is identity. This is not equal to phi. Alright. If it's not clear, you know, please ask me. But there's another. Before we quit, last question. Another problem with doing the above. This is critical thinking question here. This would be very good for those who are very fluent with matrix algebra. If you see matrices like numbers, like scalars, that's not.
No good.
It's like not being able to distinguish an apple from an orange. What else? What else is a problem with doing this? One, two.
You're making
Robert?
You're making phi asymmetric again.
Sorry?
You're making phi asymmetric.
Oh, phi is phi is a column matrix. That's a 2 by 1.
Sorry.
Yeah. So this is a 2 by 1. So let me give some hints here. This is a 2 by 1, right? And C is also a 2 by 1. It's a column matrix. Whereas m to the minus 1/2 is a 2 by 2. Can you see the problem now? Let's see somebody new. I know Colton has already participated. What is your name? Your team number?
7.
7, and your name? Nick. Okay. I think Nick also contributed more than Colton. So team 7, Nick. Let me try here. Yeah, you have. And Colton, you are team 2. Yeah. Okay, let's give Colton.
To be able to do matrix multiplication, the second dimension on the
Exactly.
first one
This
has
is
to
not-
be
You
divided.
cannot take 2 by 1 times 2 by 2. This is not a valid matrix operation. So, okay, so lecture summary, please.
Yeah.
Oh yeah. I came right on.
This is our new feeding. Yeah.
Yeah.